So you're probably wondering how we got into this situation. The answer, of course, is physics. A car turning around the corner is not as simple as you think. There's actually quite a bit of physics that takes place. In this video, we're going to demonstrate that the centripetal acceleration that occurs due to the frictional force that tires exert parallel to the ground. So as Patrick executes this right turn, we can see that there has to be some sort of force making that car accelerate towards the center of rotation. Which begs the question, what is the coefficient of friction such that a car can make that kind of turn? We can start by choosing a lens. For the purpose of this video, we're going to be looking at this through a dynamics lens, which deals with the equation, the sum of the forces equal to mass times acceleration. But now that we have that identified, what's next? An FBD, a free body diagram. How do we do that? So we'll start with the body that the forces are going to act on, the car. Now we all know that force of gravity acts on everything, so we draw that in. Now due to Newton's third law, there's an equal and opposite force acting on the car. In this case, that is the normal force. Now with these two equal and opposite forces, there now has to be some sort of force acting horizontally in order to allow for this centripetal acceleration. Well, there is, and that is the force of static friction. We use static friction to denote the friction because if it were kinetic friction, then the car would actually be sliding on the road, which is terribly unsafe in my opinion. I'm not sure about you. But anyway, here's normal force, force of gravity, and static friction. And in this clip, I want you to observe how they work in tandem. Now, when we calculate the coefficient, we're going to need to start by drawing our force equation. Sum of the forces F equals ma. Now, as you notice in our free body diagram, there's x and y components. So we have to draw a y force equation and an x force equation. Now, you'll notice F sub y is equal to 0. That's because the normal force and the force of gravity are equal and opposite, since the car is not accelerating upwards or downwards. Now, it's in the x direction that the real magic happens. So force of x is going to be m times ac for centripetal acceleration. Now when we try to draw out what forces in question are being added, and now it's in the x direction that the real action happens. So when we try to write out which of our forces are acting, you'll realize from our free body diagram, it's only really friction that's acting. So static friction is equal to ma sub c. Now in the next line, we use mu sub s as our coefficient for friction times normal force equal to m times v squared over r. So described because centripetal acceleration is equal to v squared over r. Now if you'll look back over to the f of y equations, you'll notice that n is equal to the force of gravity, which is also equal to mg. Bringing that back into the x portion of the force equation, you'll get mu s times mg is equal to m times v squared over r. Now immediately you can cancel out the masses. They really have no effect. So you're left with mu sub sg is equal to v squared over r. Solving for this coefficient of friction, we now have v squared over r times g. And you know, now that we seem to have our letters in order, why don't we try bringing numbers into it? Now beforehand we did measure the velocity of the car as Patrick turned out around the corner, and we also measured the radius that the car was making its rotation. Now if we remember our orientation from a couple seconds ago of the variables for solving for mu, we can plug in each of these numbers, the v, the r, the g, and mix them all together, and voila, you have your friction coefficient, 0.5. So now you may have been wondering before how we got into this situation. Now you may be able to explain why. Thank you for watching.